Hello everyone, welcome to week 10 of the TS session of Structure Analysis one by Professor Amit Shah. I am Trisha Chakraborty, one of the course teaching assistants. I am a PhD student at the Indian Institute of Science, Bangalore. Uh, the I begin with recapping phase 1, that was analysis of determinate structures. In week 1, we covered the basics of structure analysis, types of internal forces like bending moment, shear force, torsional moment, and axial force. Common classification of elements like beam element, frame, and trusses, boundary conditions like hinge support, roller support, fixed support, or internal hinge, etc. Then we looked at structural indeterminacy and bending moment and shear force diagram, how to draw bending moment and shear force diagram with a variation along the length of a beam. In week 2, we specifically focused on trusses. We looked at how real world trusses are idealized as 2D trusses that are easy to solve, stability of trusses, and solving the member forces in a truss using two methods: method of joints and method of sections. In week 3, we looked at the other kind of response that a structure can give. The structure can give two types of responses. One is the stress or the forced response, and the other is the strain or the displacement response. So in week 2, we looked at the forced response of truss, and in week 3, we looked at the displacement response of a truss. We started with the principle of virtual work, which can be extended to the unit load method to determine displacement, the nodal displacements in a truss. And in week 4, we looked at the displacement response of beams, deflection of beams. There are several methods. The elastic curve equation method works directly with the governing differential equation of the beam. The moment area method is an application of the elastic curve method. It is a simplified version of it. And another simplified version is the conjugate beam method. Conjugate beam method and moment area methods are used more frequently than the differential equation method, but basically all of them will give the exactly same answer. So they are just variations on each other. In week 6, we looked at a separate topic, the influence line diagram, which is the variation of bending moment or shear force or any particular kind of response as a force or a set of forces move along the length of a beam. We looked at the Mueller-Breslau principle that gives the influence line diagram in a qualitative manner, and the absolute maximum bending moment and shear force under point load, series of point loads. For example, when a car or a truck moves over a bridge, then its wheels form a series of point loads, and uniformly distributed loads greater than or lesser than the span. In phase 2, we looked at analysis of indeterminate structures, which most real world structures are actually indeterminate, because indeterminacy, the more indeterminate a structure is, the safer it is, because there are that much amount of redundancies. So in real life, when we design any structure, we make it to be indeterminate. Of course, determinate structures are easier to analyze. In indeterminate structures, we covered the topics. We reviewed the degree of structural indeterminacy. We introduce force and displacement methods, Maxwell-Betty's reciprocal theorem, and method of consistent deformation, that is a force method. In the previous three lectures, in week 7, 8, 9, we looked at force method applied to the three kinds of elements, that is beam, frames, and truss. And this now we are going to look at the displacement method. So we will start with reviewing what the degree of kinematic indeterminacy is and displacement methods. In particular, today we will look at the slope displacement method. So in week 6, we looked at In week 7, we looked at method of consistent deformations applied to beams. In week 8, we looked at method of consistent deformation applied to trusses, and week 9 to frames. And this time, today, week 10, we will look at the slope deflection method. Structural indeterminacy. Structures that cannot be analyzed using statics or equations of equilibrium only are called indeterminate structures. They require other material properties to be solved. That is basically if there are more number of unknown reactions than the number of equations of equilibrium that we can have, we will of course need some additional equations to solve the additional forces. So some material properties or some other we need to get the number of redundant reactions that we have, that many extra equations we need. So the degree of indeterminacy is the number of unknown reactions minus the number of equations of equilibrium. If the degree of indeterminacy is 0, it means it is a determinate structure. If it is less than 0, it means it is an unstable structure. If the number of reactions is less than the number of equations of equilibrium, the structure is not stable at all. And so we are not going to look at that kinds of structures, because an unstable structure is not in question. And indeterminate structures are those where the degree of indeterminacy is greater than or equal to 1. External indeterminacy, this is what we are talking about, static indeterminacy. Degree of external indeterminacy is total number of independent support reactions minus total number of available equations of static equilibrium. Internal indeterminacy is total number of internal reactions minus available equations of equilibrium. And degree of structural indeterminacy is the addition of the two. Generally, it is easier to find out the degree of external indeterminacy and the total degree of indeterminacy. So, we can find the degree of internal indeterminacy by subtracting this from this. Basically, if we can find out any two, we can know the third one. These are some examples we have looked at before. This is a cantilever beam under uniformly distributed load. At the fixed support, there are three reactions: vertical reaction, horizontal reaction, and a moment. And in a 2D plane, there are three equations of equilibrium. So the degree of static indeterminacy is 3 minus 3, that is 0. This is a cantilever beam with a prop. This is called a prop, this roller support. This gives an additional reaction in the vertical direction. So there are now total 4 reactions. But the number of equations of equilibrium remain 3. So degree of static indeterminacy is 4 minus 3, 1. This is a frame with two fixed supports at A and D. Each of the fixed support gives us three reactions, and since this is a 2D in the 2D plane, it doesn't matter whether it is a beam or a frame. The total number of equations of equilibrium remain 3. So 6 minus 3 equal to 3. This structure is indeterminate to third degree, and this is a frame with two hinge supports. There are two reactions at each of the hinges, horizontal, vertical, horizontal, vertical. So there are total 4 reactions, and there are 3 equations of equilibrium. So the degree of static indeterminacy is 4 minus 3, 1. Now, there are two approaches to solving indeterminate structures, as we have discussed before. The force, compatibility, or flexibility methods, they are all interchangeably used, the terms. So here the redundant forces are chosen as unknowns, and additional equations are obtained by considering the geometric conditions imposed on the deformations of the structure, which are also called compatibility conditions. What are compatibility conditions? Basically, uh, they ensure that in a structure there is no discontinuity, no incompatibility. That is, at any point, whether you come from the right side or left side, the limit of the displacement should be the same. The slope should be the same. If at any single point there are two displacement conditions are simultaneously existing, that means that there is a discontinuity, but that is not allowed in a structure. A structure, beams or frames or trusses, whatever, they will deform in a way that is consistent, that is compatible or continuous. So those compatibility conditions, if we impose them, we can get some additional equations that we can use to solve the redundant forces. And once we have solved the redundant forces, we end up with the determinate structures. Now the redundant forces that we have solved, we can just simply treat them as applied loads. So the determinate structure, we can solve it. We can solve the remaining support reactions, and then we can solve the entire structure. Solving an entire structure means finding out all the forces, stresses, all the displacements, slopes, and everything. So there are several methods that come under the umbrella of force methods or flexibility methods, method of consistent deformation, that we have looked at in details for all three kinds of structural elements that we have known: truss, beams, and frames. Then there is the virtual work or the unit load method, the strain energy method, the method of minimum potential energy, the flexibility matrix method. But mostly, method of consistent deformation is the only one that is important for this course, and that is what we have looked at so far. And the other approach is the displacement or the equilibrium or the stiffness method. Stiffness and flexibility are basically inverse of each other. Like, for example, in a spring, if the stiffness is K, then the flexibility will be 1 by K. So they are basically anti to each other, these two types approaches. Here, the displacements of joints are taken as unknowns, and equilibrium equations are expressed in terms of these displacements and internal loads. These equations are solved to give the actual joint displacements, from which redundant forces can be calculated. And there are three main methods that come under this: the slope deflection method, moment distribution method, and the stiffness matrix method. So today we are going to look at the slope deflection method in week 10. In week 11, we will look at the moment distribution method, and week 12, the final week, we will look at the stiffness matrix method. Of these, the stiffness matrix is actually not that easy to implement. It is kind of, I mean, the stiffness matrix method is a formulation that can be easily fed into a computer, because it solves matrix equations in coding languages like MATLAB especially. So by hand, of course, it is difficult even to invert a 3 by 3 matrix. It takes a lot of calculation, and if it becomes 4 by 4, it nearly becomes impossible by hand. So the stiffness matrix method is not that important for written exams or for MCQ exams, but the slope deflection and moment distribution methods are important. Here we look just briefly recap the differences between the two methods. In the force methods, the unknowns are taken as internal member forces or reactions, and in the displacement method, unknowns are taken as joint displacements. In the force method, to find the unknowns, compatibility conditions are written. The number of equations required is equal to the degree of static indeterminacy. While in the displacement method, to find the unknowns, we write the joint equilibrium conditions, and the number of equations needed is the degree of kinematic indeterminacy. So far, we have not looked at kinematic indeterminacy. In the last previous classes, whatever we have studied and whatever we perceive as degree of indeterminacy was static indeterminacy, that has to do with forces and reaction forces. But today we will look at kinematic indeterminacy, because going into the displacement method, that is an important topic. And the force method is suitable when ds is less than dk, that is degree of static indeterminacy is less than degree of kinematic indeterminacy. Obviously, because since the number of equations is equal to the degree of static indeterminacy, we will choose this when the degree of static indeterminacy is relatively lesser. And here the method is suitable when ds is greater than dk. Okay, so kinematic indeterminacy, degree of kinematic indeterminacy dk refers to the total number of independent available degrees of freedom of at all joints. The degree of kinematic indeterminacy may be defined as a total number of unrestrained displacement components at all joints. Now we know that this table summarizes what we already know. In 2D truss, in a 2D truss, each node we take two degrees of freedom. We take a delta x, we take a displacement in the direction x that we can call delta x and delta y. Basically, x and y are we imagine x and y as horizontal and vertical axis. They can be any two mutually perpendicular axes, but there are two independent degrees of freedom. In a 3D truss, at the joint of a 3D truss, there can be three displacements in x, y, and z direction. In a 2D rigid joint, 2D rigid joint means basically a frame joint, a joint in a frame. It can have, it has three degrees of freedom. It can move in the x direction, it can move in the y direction, it can also have a rotation in the z plane. Basically, that's the slope that we consider, because we know that frame elements can undergo all three of bending moment, shear force, and axial force. So in truss, we don't allow rotation at the nodes. That is why the members connecting two truss nodes are two force members. But in a frame, rotation is also allowed. And in a 3D frame joint, there are all 6 degrees of freedom. Basically, in a 3D plane, there are maximum 6 degrees of freedom that are possible, because there are two types of displacement and rotation. I mean translation and rotation. So translation is can be in three directions in the three-dimensional space. Of course, we do not talk about 4 dimensions. So the maximum we can talk about is 3 dimension, and there can be three translational degrees of freedom: delta x, delta y, delta z. And similarly, there can be rotation in along about three planes: sigma, about x-axis, about y-axis, and about z-axis. If this is the z-axis, then this rotation in this plane is called the theta z. Now, the degree of kinematic indeterminacy for plane truss, 2D truss, in a pinjointed plane truss, each joint has 2 degrees of freedom. Therefore, if there are j joints, then it has 2j degrees of freedom, if you consider the joints. But then there will be certain supports. If there is a hinge support at one of the joints, both the degrees of freedom are restrained at that point. So delta x and delta y are both restrained there. Then if there is a roller support somewhere, then maybe the delta y is restrained there. So if there are re number of support reactions at support, the joint displacement will not be available in that direction, in the direction of the reaction. So the total number of unrestrained displacement components will be 2j minus re. So if there is one hinge support and one roller support, then RE will be 2 plus 1 3, and if suppose there are 6 joints, so there will be the degree of kinematic indeterminacy we can find out by 2 into 6 minus 3. In a space truss, similarly, the degree of kinematic indeterminacy is 3j minus RE. Here it's 3j minus RE, and for rigid jointed space frame it is 6j minus RE. Now this 6 is important here. Uh, and another thing, for the space truss there are 3 degrees of freedom. For the rigid joint frame there are also 3 degrees of freedom. But but these three do not represent the same thing. In a truss, these three represents the delta x, delta y, and delta z, while in a plane frame, it represents delta x, delta y, and theta z. And in a rigid jointed space frame, there are 6 degrees of freedom, like we said here, and minus RE. And this RE, you have to be careful that how many reactions a particular kind of support provides. For example, a hinge support in a 2D plane provides two support reactions in the x and y direction, but a hinge support in a 3D space provides three support reactions. So that we have to be careful about. In the above analysis, all members are considered actually inextensible, and all above displacements are elastic displacements. There's a special case in a rigid frame. If some members are actually rigid, then axial displacements in such members may not be available. Hence, the degree of freedom will be reduced. I mean, we assume that in a frame element, it can undergo axial displacement. Deformation. It can undergo shear deformation, and it can undergo bending. But if there is one member that is mentioned that this cannot deform axially, so at that point the delta x will be restrained. So if m dash dash is the number of axially rigid members, this you have to subtract, because that is, if there is one axially rigid member, one degree of freedom is subtracted. If there are two actually rigid member, 2 degrees of freedom will be subtracted. So dk will be 3j minus re minus m dash or dash dash, or 6j minus re minus m dash dash. Let us look at a few examples. Determine the degree of kinematic indeterminacy for the given cantilever if the beam is actually flexible, if the beam is actually rigid. Now there are two joints, and how many how many degrees of freedom does each joint have? Three, right? Because axial shear in this displacement in this direction, displacement in this direction, and rotation in this plane, like out of the plane or into the plane. So three. There are two joints, one, two. 3 into 2 is 6. If this beam had no support reaction, then there would be 6 degrees of freedom. However, there is a fixed support. And what does this fixed support do? It restrains the vertical displacement, horizontal displacement, and z rotation in at A. So that it gives 3 reactions. So 6 minus 3 is 3. So here the degree of kinematic indeterminacy, if the beam is actually flexible, is 3. But if the beam is actually rigid, then basically the delta x here is not free. So the b, so this has only 2 degrees of freedom, vertical displacement along b, and the slope along b. The When the member is actually rigid, we want to find out for the or simply supported beam. There are two joints. So 3 into 2 is 6. Without any support reactions considering, we would have 6, and there are two support reactions basically. 1, 2, 3, 4. There are four support reactions. So 2, if we consider AB as actually rigid, then decay will be the same as previous case, because actual displacement is already restrained by reactions. There is no difference. I mean, it doesn't make a difference whether the member is actually rigid or flexible here, because anywhere the delta x at neither A or B we are allowing. Here the delta x at B was being allowed. That is why it made a difference. So the decay varied whether it is actually flexible or rigid. Here it remains 2. There is another special case that in rigid jointed frames, some of the joints may be hybrid, then additional degrees of freedom will be available. Hence, decay will increase. For 2D rigid jointed frame, decay is 3j minus re minus m dash dash plus rr, where rr is basically the what hybrid joint is, where more than two members come and meet. So if m dash members meet at a hybrid joint, then rr will be sigma m dash minus 1. I mean, however many joints there are, we have to add. How many are the hybrid joints are, we have to keep adding them. And so for a 3D rigid jointed frame, decay is 6j minus re minus m dash dash plus rr. J is the total number of joints, including rigid joint, hybrid joint, supported joint, and unsupported joint. Basically, as many joints there are. M dash dash is the number of actually rigid members. M dash is the number of members meeting at a particular hybrid joint. So RR is a sigma M dash minus 1. And for 2D, for 3D, we earlier for the truss indeterminacy we studied that RR is 3 into, sigma 3 into M dash minus 1. Let us look at this. The number of independent degrees of freedom for a two-span continuous beam of uniform sections. Basically, this has 1, 2, 3 joints, and 3 into 3 degrees of freedom open. And then there is one fixed support that has three support reactions, and there are two rollers that give one reaction each. So there are 5 reactions. So the degree of kinematic indeterminacy is 3 into 3 minus 5, that is 4. And the kinematic indeterminacy of a frame, let us see. So this is a hybrid joint, this hinge. So J is 4 because there are 4 joints. The support number of support reactions is 3 from this fixed support and 2 from the hinge support, so 5. And at this hybrid joint, two members are meeting, right? So RR is sigma m dash minus 1, 2 minus 1 is 1. And the degree of kinematic indeterminacy, and there are no actually rigid members mentioned, so the formula reduces to 3j minus re plus rr, that is 8. And here there is a beam. Again, there is a internal hinge. So the J is 3 because there are 3 joints. The number of support reactions is 5 because 3 from here, 1 from here. M dash dash is 0 because said that considering the beam pool flexible. And M dash here is 2 because 2 members are meeting at the internal hinge. So RR is 2 minus 1, 1. So DK is 3 into 3 minus 5 minus 0 plus 1, that is 5. And this is a, I mean, rigid jointed frame. Find degree of kinematic indeterminacy. Now it says that it is rigid. So basically, we have to consider there are 1, 2, 3, 4, 5, 6, 7, 8, 9 joints, and the number of reactions here is, here there are 3 reactions, here there are 2 reactions. From fixed support we have 3 reactions, from hinge support we have 2 reactions, and this is not a regular roller support. And in a regular roller support, only one reaction is provided in the vertical direction, but a roller with 3 or more wheels also prevents the rotation. So it is allowed to move in this direction, but it is not allowed to move in this direction, and not allowed to rotate. So there are 2 reactions coming here. So RE is 3 plus 2 plus 2 equal to 7, and M dash dash is the number of actually rigid members. Basically, this, and this. And so decay is 3 into 9 minus 7 minus 4. There is no internal hint, so that RR term is 0. So 27 minus 7 minus 4, there is 16. There are 16 degrees of freedom. Basically, kinematic indeterminacy is the number of free degrees of freedom. Now, and there is another. Consider 2D rigid frame. If there is a rigid frame, then the number of joints is 10, 1, 2, 3, 4, 5, 6, 7, 8, and 7, 8, 9, and 10. And then the number of reactions is 3 plus 2 plus 1, that is 6. And here, from the formula, we can find that there are 24 degrees of freedom. Now we move on to the slope deflection method. Now that we know the degree of kinematic indeterminacy and we know about the degrees of freedom, we move on to the slope deflection method. In the slope deflection method, the relationship is established between moments at the end of the members and the corresponding rotations and displacements. The slope deflection method can be used to analyze statically determinate and indeterminate beams and frames. It can also be used to analyze determinate structures, but there is no point doing that because it will unnecessarily complicate the problem. We can, in determinate structure, we can simply solve the support reactions and move on to the internal forces and internal displacements and everything. But now, if a structure is given to you, the first thing to see is whether it is indeterminate or determinate. If it is determinate, the solution is fairly straightforward. But if it is indeterminate, then the next thing we are going to do is calculate the degree of static indeterminacy and calculate the degree of kinematic indeterminacy. And and whichever is lesser, if the degree of static indeterminacy is less, we will try it for the method of consistent deformation that we did earlier. We will take the redundant forces as unknowns and we will solve using compatibility conditions. But now, if the degree of kinematic indeterminacy is lesser, we will try for the slope deflection or moment distribution method, whichever you are more comfortable with. And we will take the joint, the displacements and rotations at the joints as are unknown, and using equations of equilibrium at each joint, we are going to solve them. And then we are going to, now that, and once we have the displacements and rotations at the joints, then we can move on to the forces and displacements of the entire members. First, we look at the sign convention. The clockwise end moments are taken as positive and anti-clockwise end moments are taken as negative. It is fairly straightforward. Here, MAB is in the anti-clockwise direction, so it is negative, and MBA is in the clockwise direction, so it is positive. For slope or rotations, again, clockwise rotations is taken as positive and anti-clockwise rotations are taken as negative. So here, this theta A is in the clockwise direction. It is rotating like this. Theta B is like this. Theta B, that at the B joint, the thing is, the beam is rotating like this. So it is anti-clockwise. It is negative. Theta C again is in the clockwise direction, so it is positive. Of course, this is a very exaggerated version. We will never see a beam deflecting so much, but we draw a representative diagram just to see, like, if a loading is given, we try to visualize the manner in which it will deflect, and we can see whether it is clockwise or anti-clockwise. But it doesn't matter, you can assume that all its rotations are clockwise, and then the result will automatically come positive or negative as per whether it is actually in the clockwise direction or in the anti-clockwise direction. And for deflection or settlement, positive deflections are taken to be the ones which produces clockwise rotation to the member. Here, If there's downward deflection, it provides clockwise rotation to the member, right? So here the downward deflection is taken as positive, and negative deflections are those displacements or deflections that will be negative, which produces anti-clockwise rotation to the member. So here, see here, this is displacement. Basically, displacement are not can not just be in this plane; it can also be in this direction. So take we just see how the member is rotating according to that deflection. For example, here, if this displacement is taking place, the member is rotating like this in the anti-clockwise direction. So we will call it a negative deflection. We will start by deriving the slope deflection equations. We will consider a segment AB of a continuous beam as shown in the figure. The slope deflection equations are derived by superimposing the end moments developed due to applied load, rotation at joint A, rotation at joint B, and settlement of support B with respect to A. So, this is the AB segment. There is a moment MAB here and MBA here. AB is at A and BA is basically at B. And here we see that the span AB is subjected to a combination of multiple loading as shown above. In the beam shown in figure 1, the fixed end moments at A and B will be MAB and MBA. In the beam shown in figure 2, in this here, there is the joint A is rotating by angle A, theta A. So the fixing moments at A and B will be MAB is 4 EI by L theta A and MBA will be 2 EI by L theta A. And then in 3, there is a theta B here, so due to that, the MBA will be 4 EI by L theta B and the MAB will be 2 EI by L theta B. And if the support B settles by delta corresponding to A, then the A member is rotating, and in the clockwise direction like this it is rotating. So there are the fixed end moments produced at B will be MBA is minus 6 CI delta by L square and MAB is minus 6 CI delta by L square. That's the final moment at end A and B due to all the above. I mean, we are using the principle of superposition, linear superposition. We can add all four of these effects, and we will get that MAB is MAB bar is a fixed end moment plus 4 EI by L theta m plus 2 EI by L theta b minus 6 EI delta by L square. And from that, this and from that we get two simplified equations. We can write in this manner: MAB is this and MBA is this, and these are known as the slope deflection equations. The steps: we consider each span fixed and find fixed end moment for each span due to given loading. Each span means if there is a span between any two supports, we will consider as fixed. We will consider both ends are fixed, and we will find the fixed end moment for each span due to the given loading. There can be any kind of loading inside the span. If any support settles, then do not find fixing end moment separately because we have already considered its effect in derivation of slope deflection equation. Take theta and delta as unknown and write slope deflection equations for end moments. Find joint displacement theta and delta by using moment equilibrium equations and shear equations at the joints. The number of equilibrium equations is equal to the number of rotational displacement components, and the number of shear equations is the number of translational displacement components. Then we will substitute the now that we have solved the theta and delta, we will substitute the values of unknowns in slope deflection equations and determine the end moments. Then finally, once we have that, we can draw the bending moment diagram by superimposing end moment BMD and free BMD for each span. Thus we can draw it each span wise, and we will see that it will come a coherent continuous BMD or SFD, the kind we are expecting. Here, let us look at a few examples. This is a beam. This has two spans basically for AB and BC, because loading doesn't matter here. I mean, of course, here we this and this we won't say call separate spans. Separate spans are where there is a change in support reaction. So in span BC, MAB is minus PL by 8 and MBA is PL by 8. We can see from this formula. If we put it here, we can see this. And in span BC, MBC is MBA, MAB, and here MBC is minus WL square by 8. Here P is 60, so 60 into 6 by 8 is minus 45 and plus 45. This will be span AB actually. MAB is minus 45, MBA is plus 45. In span BC, the MBC is minus WL square by 8 and MCB is plus WL square by 836. Now we will write the slope deflection equations. This MAB bar, there are formulas in books that the to remember the fixed end moments for common fixed beams. Like in a fixed beam, if there is there is a load in the midpoint, if there is uniformly distributed load, or if there is a point load at distance A from one end, B from one end, there are certain formulas that you have to remember for this MAB bar and MBA bar. Then the unknowns here, what are the unknowns here? Basically, the rotation and displacement here is restrained, the rotation and displacement here is restrained, the displacement here is restrained, but the rotation here is open. So theta B is basically my only unknown. And here we see that we just write first we imagine that all of them are free. So we have theta A, theta B, theta C, delta A, delta B, delta C. Then we will find out that theta B is the only free one. So for member AB we write the two reactions MAB, the two equations MAB and MBA. From that we get two equations. From member BC we get another two equations MBC and MCB. And then we solve these. We have to solve only theta b. Theta b is unknown because theta c is 0, delta is 0, we know that. So joint equilibrium condition, what do we do? We here take that we have unknown theta b, that is rotational displacement. Hence one joint equilibrium condition is required because we have one unknown. So at joint b we impose a joint equilibrium equation that there can be no net moment, since we know that at a roller support there is no moment given by the roller support. Minus MBA and MBC have to add up to 0. That is what is our equation, joint equilibrium equation. So MBA plus MBC is 0. Which sign we will put the expression of MBA and BC we obtained. We adding them, we see that theta B is minus 6.75 by EI. That means that it is in the anti-clockwise direction because we had assumed that clockwise rotation is positive. Substituting the value of theta b in the slope deflection equations, we get the fixed end moments MAB, BA, BC, and CB. And now that we have those, we have kind of these two spans. We know the MBA and MAB, and we know the reaction A and reaction B we have to solve basically, because now that the given, now the loading in this span is the actual loading on this span, that is a 60 kilonewton, and then there are two end moments that we calculated. According to that, we can find out RA and RB1. B1 because B has basically two reactions from both the spans, so that we can solve using normal equations of equilibrium, like sigma Fy equal to 0 and moment about any one point should be conserved. Just now we are just considering a beam that has that is a simply supported beam span that has two end moments as loads, and there is a point load. So we solve RA and RB1, and here we solve RB2 and RC. And now we can see that we can use any of these equations. We will see that ultimately RA plus RB plus RC has to equal the total force applied, is 60 plus 12 into 6. And now we can draw the bending moment diagram, because this is our beam. We know the reactions, we know the end moments. Here there's end moment, here there's an end moment, and here there is no end moment. Why? Because we already, this was our equilibrium condition, that MBA and MBC should add up to 0, because at a roller support there can be no external applied moment. But these were fixed supports, these were actually fixed supports here. In a slope deflection method, we assume each support to be fixed, and if there is one support is not actually fixed, it can allow rotation, we will equate the moment to be 0. But A and C were actually fixed supports, so they do actually give a moment reaction. So these are the moment reactions and these are the applied forces. And just superimposing the bending moment diagram due to the two, we get this bending moment diagram of the entire beam. We look at another example. So here there are three spans, AB, BC, and CD. Fixed end moments in for MAB and MBA bar will be 0 because there is no loading. For CB and NBC, like we saw earlier, it is WL square by 12 minus and plus positive respectively. And MCD also MCD and MDC will also be WL square by 8. Now the slope deflection equations we have to write for all three spans. For AB we write this, but at A we know that since this is a fixed support, theta A and delta is 0. At B, delta B is 0 but theta B is free. Then for member BC, delta B is 0, delta C is 0, but theta B and theta C are unknowns. So we write two more equations here. And for member C, theta C is free, delta C is restrained, but delta D and theta D are both unknowns. So we have total four unknowns: theta B, theta C, theta D, and delta D. And we have now we have six slope deflection equations here. So differential equations are moments at each end, and the joint equilibrium equations we write here is first we will consider joint equilibrium at joint C. What will we do? We will write that MCD plus MCB equal to 0. At B also we will write the same thing, MBC plus MBA equal to 0. And so from that we will get an equation of theta B and theta C, and for joint equation of equilibrium C we will get uh, theta B and theta C. So solving the two simultaneously, we have them solved, and from here we can again find out the delta and theta of D as well. So we consider the free body equilibrium of each span subjected to n moments like this. Again, what we do is we take each as a simply supported beam with reactions at both ends, RA and RB1. We apply the moments that we have found out here, and then we apply the normal equations of equilibrium to find out RA, RB1, RB2, RC1, RC2, and we get this. These are the solutions. And now we can, now that we have this, we know the end moment, we know the support reactions at each support, and we can draw the bending moment and shear force diagram. This is another example. We are analyze a continuous beam as shown here. So here there is another thing, support B settled down by 5 mm. So far there was no settlement in support, so this term was not being included in the equation. So 1, 2, 3, we have three spans. For member AB, MAB is MAB bar plus 2E into 2I by L, because here the moment of inertia of each is not the same, into 2 theta A plus theta B minus 3 delta by L. MAB bar is 0, theta A is 0, and delta is plus 0.005 because it produces clockwise rotation, because it is settling like this. So MAB is 4 EI by 3, 0 plus theta B minus 3 into 0.005 by 3. MAB we get this equation, and for MBA also, MBA bar again is 0 because in that span there is no loading, right? So basically there is no loading in this entire beam, but since there is one support settling, there will be certain reactions and reaction forces in the members developing. We have MAB and MBA expressions. Next we move on to member BC, where MBC bar and MCB bar are again 0, and this term will be 2EI into 2.5 I by L, because here this moment of inertia is given as 2.5 I. 2 theta B plus theta C minus 3 delta by L. Here see the delta B, since it is since it is reflecting this in span BC, it is giving an anti-clockwise movement. So this is minus here, minus 0.005. And the MBC and MCB expressions we get in member CD, MCD bar and MDC bar are again 0, and theta C, theta D, and there is no, here the theta is delta is again 0 because the delta is 0 because in the span CD there is no settlement. We forget that there is settlement is B when we are looking just at the span CD. And now what are the free degrees of freedom? At A, delta and theta are both restrained. At B, we have theta B free but delta B is restrained. At C, delta C is restrained but theta C is open to rotation. And at D again both are restrained. So theta B and theta C are my unknowns. So here we see that for equation of equilibrium, we consider the joint equilibrium of joint B, MBA plus MBC is 0. So 2.67 EI theta B minus 6.67 10 to the power minus 3 EI plus 2.5 EI theta B plus 1.25 EI theta C plus 4.6875 into 10 to the power minus 3 ei. From that we get one equation in theta b and theta c, and then of course we will consider again the joint at equation. I mean, we have to also ensure that the moment here at c is zero, right? Because see, moment at a and d are not zero, because since they are fixed support, they actually do provide a moment reaction, but b and c don't. So we will get two joint equilibrium equations. One is that the net moment at b is zero. Another is that the net moment at c is zero. So the net moment at b is zero. We got this, and from c is zero we get this. So we solve these theta b and theta c simultaneously. There are two unknowns and two reactions. We get the rotations. These are in radians, of course. Then we find final end moments. We already had the expressions in terms of theta b and theta c. Putting those, we find the 1, 2, 3, 4, 5, 6, all 6 end moments. And we will see that, of course, here MBA and MBC will add up to 0, and MCB and NCD add up to 0, because that was the condition we imposed to find out the theta B and theta C. And now the support reactions, we will take the three spans as simply supported. We will put the end moments. We will put the given loading where there is no loading, and due to delta there will be no loading here. So the reactions will be equal and opposite here, basically, because since none of them have any kind of transverse loading, RA and RB1 have to be equal and opposite like this. RA is 25.75 upwards, RB1 is 25.75 downwards, and like this RB2 and RC1 have also to be equal and opposite, and similarly these two. So after that, once we have three spans of all forces and moments are known to us, all external forces and moments, so we can find out the bending moment and shear force just like we do. Here we can see that this jump in the shear force diagram is equal to the jump here, equal to the net reaction force here, that is RB1 plus RB2, that is 39.57. So this jump will be 39.57, and this jump will be RC, that is 21.236. And the bending moment diagrams are straight lines because there are no uniformly distributed load or anything. If there are only point loads, concentrated loads, then the bending moment diagrams are joined by straight lines, as we know. Okay, so then this is another, this is a beam with an applied moment here. So fixed end moments here, we have to take two spans here, AB and BC. The MAB bar is minus PL by 8 because the 32 kilonewton is at the center. So if it is at the center of a fixed beam, the fixed end moments are PL by 8, minus PL by 8 and plus PL by 8. So the MAB bar is minus 32 into 3 by 8, that is minus 12, and MBA bar is plus 12 kilonewton meter. MBC, this is due to a moment, the fixed moment due to a moment. This is also a value that has to be remembered for a fixed beam. If a concentrated moment is applied, the MBC bar and MCB bar are basically M naught by 4. This is clockwise moment, so that is why it is positive. If it was anti-clockwise moment, the fixed end moments would be negative. Slope deflection equations for both the spans. For AB, we write MAB equal to MAB bar plus 2E into moment of inertia by L, 2 theta plus 2 theta A plus theta B minus, here there is no delta, so that will not be there. And MBA we write the same way, minus plus 12 plus 2 EI theta B plus EI theta A. Now again let us look at what are our free degrees of freedom here. There are, since there are three joints A, B, and C, the total degrees of freedom would have been 6. But at C, both the degrees of freedom are translational, rotational, restraint. At A and B, the translational degrees of freedom, delta A and delta B are restraint, but theta A and theta B are free. So theta A and theta B are basically the two unknowns that we want to solve. Now, for member BC, we write MBC and MCB equal to these two. And here, what are the equilibrium joint equations we will write? At A, there is only one moment MAB, but since A is not a fixed support, since A is a roller support that does not provide any reaction moment, so MAB by default has to be 0. This MAB that we have obtained here has to be 0. And at B, MBA plus BBC have to be 0. So MAB equal to 0. From that we get one equation in theta A and theta B, and joint equilibrium at B is MBA plus MBC equal to 0. So we get two simultaneous equations in theta A and theta B. Solving them, we get these. And the final n moments we can again solve using that. MAB is automatically 0. BA and MBC are equal and opposite in sign, and MCB is this. This is the moment that is applied by the fixed support on the beam, and the before solve the support reactions of each span. In this span, there is one applied moment and there is one applied force, that is 32 kilonewton externally, and one internal moment MBA, and the reactions we solve. And here there is one concentrated moment applied, and there is one internal moment MBC and one support moment MCB. So solving those, we get RA, RB1, RB2, and RC. And again, the way we have been doing, we draw the shear force diagram and the bending moment diagram. This jump is equal to 32 kilonewton. This jump is equal to RB, and this is equal to RC, and this is the bending moment diagram. Superimposing the two basically. And we look at one last example here. Then we analyze the continuous beam as shown in figure by the slope deflection method. Same problem, basically in a different kind of loading conditions. We take AB and BC as our two spans, AB, BC, and CD. So what are the free support free reactions? Here we have four joints, A, B, C, and D. This is not a joint, but there is a force applied. This is not necessarily a joint. Only the support points and the end points are the joints. So there would have been 2 into 4. There is 8 degrees of freedom. But at A, both are restrained. At B and C, the verticals are restrained. So theta B, theta C, and delta D and delta C are our delta D and theta D are our unknowns. So for this part, the fixed moment will WL square by 12 minus and plus respectively, 40 into 4 square by 12 here. For this part, this 80 is no longer at the center, so we use this formula. This formula is PA square B by L square. MBC bar and MCB bar is PAB square by L, and PAB square by L square, and PA square B by L, where A is this distance. A is the distance from the left end and B is the distance from the right end. So 4 and 2 respectively. So the MBC bar is minus 80 into 4 into 2 square by 6 square, and MCB bar is 80 into 4 square into 2 by 6 square. And now we write down the slope equations. MAB is MAB bar plus 2EI by L, 2 theta A plus theta B. Here theta A is 0 because it was a fixed support and there is no settlement, so delta is also 0. So this is just an equation in theta B. Then MBA is an equation also in theta B. MBC is MBC bar plus 2EI by L by 6 into 2 theta B plus theta C minus 3 delta by L. There is no delta, but theta B and theta C are both unknowns. So MBC and MCB are simultaneous equations in theta B and theta C. So, and the equations of equilibrium that we write are MBC, and the total moment at B and the total moment at C have to be 0 because hinge support does not provide any rotational restraint. So MBA plus MBC equal to 0, MCB plus MCD equal to 0. So from that we get two equations in theta B and theta C, and by solving them simultaneously we get the values of theta B and theta C. We need not actually find out the value because while finding the fixed moment we will need EI theta B and EI theta C, so we can also keep it at that. And the final end moments will be MAB is this, MBA will be this, MBC is MBA and BC will be equal and opposite in sign because there is no net moment at B, and similarly MCB and MCD will also be equal and opposite in sign. And the support reactions here, we take the two spans, we have one up moment here, one internal moment here, one reaction moment here, and UDL applied. So we can solve RA and RB1 using normal equations of equilibrium. And in the other span, we have uh, this one internal moment, and there are applied loads, and there are two support reactions. So we solve RA, RB1, RB2, RC, and now that we have that, we have all these, we have all the loading conditions and reactions, we can easily draw the shear force and bending moment diagram. The maximum simply supported moment in AB is for a 40 into a, as you know, WL square by 8 because it is a UDL, a simply supported beam under UDL has a parabolic nature, and the maximum is WL square by 8, and the maximum simply supported moment is B is PAB by 6. That is a formula that you can remember, otherwise you can just find it out. And this is how the shear force diagram will look like when there is uniformly distributed load. The shear force diagram is a straight line, otherwise it is a straight line with a slope. And if there are only concentrated loads, the shear force diagram works in uniform straight lines with jumps. So there will be a jump here because of RB, there is a jump here due to applied 80 kilonewton. there will be a jump here and a jump here due to concentrated loads. And this is the bending moment diagram, which with parabolic nature, because when there is UDL, the nature of the graph becomes parabolic, and the elastic curve and the displacement curve is like this. That is not important right now because it needs some perspective and some experience to be able to predict how the elastic curve will look like. So that's all. And to summarize, the slope deflection method, basically what we did is, so in the slope deflection method, basically what we did is, we first we need to find out the degree of kinematic indeterminacy. That is basically the number of unknown number of unknown rotations or displacement that we have to solve. We start by assuming that each degree of freedom is free. Then we see how many are restrained actually. Like for a fixed one, the rotation and displacement are both, rotation and translation are both restrained. So that is how we find out the degree of kinematic indeterminacy. Those are a number of unknowns that we have to solve, and each span between each two supports we take as fixed. So we find out the fixed end moments due to the given loading on the beam. For that, some formulas have to be remembered, and then we have just two slope deflection equations to be remembered for a fixed span. The AB, MAB, and MBA. Those two expressions we have to remember. They depend on the fixed end moments at AB and BA due to the given loading, and it depends on theta A, theta B, and the relative the deflection between the two. So we write those down. For each span we write that down, and then we apply the joint equilibrium equation, that is basically that acts as at joints where rotation is allowed, there can be no movement. So the net moment from all the members meeting at that point should add up to zero. For in a frame element, if there are three members of a frame meeting at a joint that is not fixed, that is rotationally free, then all three have to add up to zero. Those are the equations that we can get, and getting those equations, we will see that we can get as many equations as the number of unknowns. So we will solve the theta A, theta B, or whatever, delta A, delta B, whatever our unknowns are. Then we will go back to each segment. Now that we have the applied moments or the internal moments, we uh, we can find out the reactions, and then we have the entire loading pattern including reactions of the beam. Then we can draw the bending moment shear force diagram, which is a continuous response of a structure. So that is how we end. And this, the sign convention is important. And that in the next class we will look at the moment distribution method, which is another displacement stiffness method. And the last in week 11, and in week 12 we will look at the stiffness matrix method.